Our guest tonight is Professor Cornelia Lang from the University of Iowa Department of Physics and Astronomy. I got it right. And she's going to talk about the University of Iowa and the space program and how involved Iowa has been for many, many, many years. Thank you and welcome.
Great, thanks so much, and thanks for coming tonight. I want to give a little bit of thanks in my presentation, well, a lot of thanks to the Department of Physics and Astronomy. I have almost nothing to do with anything you're going to see tonight personally, other than I have a real interest in all of it. It was a highlight of my career to come to a department that had such a long history, and I sort of had to write it in my own head. I also read the really excellent biography of James Van Allen called The First 9 Billion Miles or something like that. Abigail Forstner, I'm sure they have it here at the public library. It's an excellent read, so if you haven't read it, I try to give it to graduating students of mine when they finish working with me as sort of a tribute to their time in our department. So I want to thank members of the Physics and Astronomy Department. We have a former student here tonight, and we have a longtime employee of our machine shop. So if you have any questions about the technical and mechanical and building aspects of some of the space machinery we talk about tonight, Mike might be able to help answer questions. But one message I want to get across to you guys tonight, and I think it will come across in the photographs, is that this kind of work is not done by an individual. We are going to focus tonight a little bit on the late Professor James Van Allen because he was such a visionary thinker. We're also going to hear about selected professors who not only had vision for individual missions, but then also led teams of students and staff and engineers. But I do want to emphasize the team aspect because none of this stuff, there's no single person on Earth who could do the kind of complex work that it takes to actually design, build, test, launch, track, and then digest the data. These are major undertakings, each of them on their own. So I want to thank, again, Department of Physics and Astronomy, members of the Space Physics Research Group, and that's a very vast number of people, the UI Special Collections, the Pentacrest Museums, and the Henry County Heritage Trust, where we got some artifacts from the original Van Allen homestead, and I'll show you a little bit about that tonight. We built an exhibit in 2015 and 2016 that was then on display for an academic year in the basement of the old Capitol, and this was our logo. And so if we have time at the end, I'll show you a few pictures of what that exhibit looked like and kind of how we made it, because that itself is kind of a fun story. So this is what I want to do, and I may not have time to do everything, but like a good teacher, I know when to, I can flip through some of these slides quickly. But I'll start by just sort of talking a little bit about what the department at University of Iowa was like around 1950, and then I'll give you a little bit of backstory about James Van Allen. It's kind of like the crib notes for the biography, at least the first few chapters. And then we have a couple of things organized by time. So we'll spend some time talking about 1958, which was a big year in space exploration. This year, of course, is a really big year because it's the 50th anniversary of Apollo 11. But this was a big year in terms of even getting to the point where we could put humans in space and land on another body. And I'll talk about sort of my favorite years when I have learned about this were the years in which pretty much the University of Iowa was acting as if it was a NASA center. And so it was a very unique moment in space history in that there were almost no other places on Earth that were doing all of these kinds of things in terms of getting instruments, scientific instruments ready for space. And then around 1975, and Mike told me a little while ago, he arrived in about 1979 to the department. This was an era in the late 70s, not exactly 1975, but in the late 70s, the department kind of changed to a model where they would build components of things that would go in space, and then they would be shipped off for the integration, testing, calibration at a major NASA center. And that's more or less the mold we're in now. And of course, no historical talk ends at a particular place in time. And in our department, we of course have a long tradition and legacy of space projects going forward. And so I want to end with a very upbeat, energetic message that this is not said and done just because Professor Van Allen has passed on and some of his proteges have retired, but we are a very active group now doing this work. So let me start by just showing a couple-minute video. It was really nicely done that the university made for us, and that might just give you a summary of
The University of Iowa has a long tradition of leadership in exploring space in our country. Professor James Van Allen, he's really known as the father of scientific space exploration.
Between 1951, when Professor Van Allen arrived, and 1975, University of Iowa was the place where spacecraft instrumentation, design, construction, tracking occurred. It was the place in the world.
And the University of Iowa has maintained a very strong leadership role in space exploration.
My research focuses on the very core of the Milky Way galaxy. When you look out in the universe, especially at very, very far distances, you are primarily seeing the centers of galaxies. And so if we can understand our own galactic center, we can only hope it will inform us about these more distant systems that populate the universe. That's the
I
talk
study
next month.
the sun and how the energy from the sun flows through the solar system and impacts both the evolution of the solar system and the Earth. The one object in our solar system, and admittedly a very important one that we've never visited, is the sun. So currently, researchers here at the University of Iowa, as well as a team of scientists and engineers across our nation, are working on this billion-dollar mission, Solar Probe Plus, to send a probe to the sun to actually sample the outer edges of the sun's atmosphere, what's called the solar corona.
The trademark of James Van Allen, any story that you hear from his early days includes undergraduates knocking on his door saying, I want to work on the space program with you, and him saying, please join. That has remained a hallmark of our department, involving students, undergraduates and graduate students, even from other departments, in the exploration that we're doing.
The first time I came into this lab, I was just overwhelmed. It was, what's this, what's that? Gradually over time, I learned what each and every single piece of this lab does.
I'm looking at galaxy clusters and the interactions that they partake in. I wanted to help out with this, and that's exactly what I'm doing now as a freshman at the university.
Every day I come in and they teach me something new. It's amazing. It's one of the greatest feelings in the world.
The Solar Probe Plus mission will launch in the summer of 2018. So it's just a few years away. It's a really exciting time right now in space physics and here at the University of Iowa.
Yeah, so that mission launched last summer, and usually the tradition with these space missions is after they launch, they name it after the person, because there is a high risk of failure on launch. And they don't want any one particular name associated with a crash. And so Peter, you're absolutely right. It is named after Gene Parker, who's an amazing theorist. I think did a lot of his work at University of Chicago. And so it's now called the Parker Solar Probe, and we have an active program in that. Okay, so let me set the stage here. 1955, this picture was taken of the faculty at the Department of Physics and Astronomy. This is in front of McLean Hall. McLean Hall, which was where the physics department was in those days. And so you can see that this is Professor Van Allen, who had been recruited back to the University of Iowa to lead the department. And this is a little bit of a different model now than we use for hiring the head of a department. Usually the head of the department these days comes up from within, although sometimes when you want big visionary change, you bring in an external person. And that's exactly what this department wanted to do. The field of physics was headed in the direction of kind of nuclear and what will now be called particle physics. There were a lot of mathematical physics in the department. But James Van Allen was doing something that very few other scientists in the country were doing, really in the world. He was interested in studying the particles that primarily come from the sun, but also can come from other energetic sources in the universe called cosmic rays. And he was interested in what their distribution was as a function of height above the Earth's atmosphere. And I'll show you how he tried to measure this. And so right around in the early 50s, he was working on the East Coast as a research scientist just out of the Navy as a naval officer. And they called him up and said, we think that your bold direction in space physics would be really interesting for our department. Would you be willing to come back and lead our department? It was probably one of the most important decisions this university ever made. Let me just say a few words about his connection to Iowa, because he grew up in Mount Pleasant. He is an Iowan through and through. He was one of 4 boys in a family, as you can imagine, that prioritized education. And there's all sorts of amazing stories in the biography and also just in stories that I've heard and that have been related about how strict the family was. The boys were to read. They were almost rarely let out to do social activities. And when they weren't reading, they were playing with a single erector set that we have, that we had on display. It's the Henry County Heritage Trust, but it's a classic 1929 steam shovel model, and it was so beautiful. We had it in the exhibit, and it was really fun to look up. All the pieces were there. They were all kept perfectly, but the 4 boys worked through that set. The boys, their dad got them an old car, and they would spend time on the weekends figuring out how the radiator and all the mechanics of the car worked. In high school, he was a right-hand young man to his physics teacher, and the physics teacher even gave him a key to the physics labs. And on the weekends, he would have permission to go in and try some of his own experiments. So Van Allen was a genius in that he was a tinkerer that had great innovative ideas, and he also worked hard. He was not a genius in the kind of sitting with a piece of paper and having these brilliant insights. And this is a theme that you'll see over and over again in the way that the work he did looked. He went to Iowa Wesleyan and studied physics, and he worked with Professor Coulter, who was studying the Earth's magnetic field. And this professor was going to different latitudes to look at different properties of magnetic measurements. And he invited Van Allen. This is sort of a different era. He was going to go on a 2-year expedition to the Antarctic to make measurements at low Earth latitudes. And so he invited his preeminent student to come with him, and the Van Allen family said no. They said, you need to stay here, you need to read, you need to focus on getting your graduation finished. And so the benefit, so it was totally, I think, not a pleasant moment in Van Allen's life, but he did what his family said. But the best part about it was he had to take over teaching all the physics labs for his faculty member. And so he actually got amazing skills by staying at home, finishing his degree on time, and doing a lot of teaching. And again, a lot of lab work was part of his requirement. Then he came to the University of Iowa for graduate school in physics, and he was actually very interested in moving away from the magnetic field work, although he had a foundation in that he had done with his undergraduate advisor. And he was moving into this very exciting area of nuclear physics. And so when he got his PhD at University of Iowa, then he took a job on the East Coast at the Carnegie Center for Terrestrial Magnetism. And then the war broke out, World War II. And so he was quickly recruited to work with Dr. Tuve at the Advanced Physics Lab at Johns Hopkins. And they were working on the components of the proximity fuse, which was screwed into the top of artillery shells, and it would help detect with more accuracy an oncoming target. Previously, you would just let the shell explode and hope it hit something. But in this way, there was a radar signal sent out, and if it came in contact with something, then the shell would explode. And it was one of the reasons that historians will say this was a major contribution to winning in the Pacific at the end of World War II. And Van Allen made some critical contributions to the design and functioning of the miniature electronics up here in the nose cone. And for this work, the University of Iowa awarded him with the University of Iowa Distinguished Veteran Award in 2016. Now, one of the reasons I mention this is a whole story in it to itself, which we're not going to talk about tonight. But to connect back to University of Iowa and the space exploration, the vision to do space exploration is because of his time in service that he gave to the Navy, they awarded him with something that I don't think many people have now, which is a small stipend to do research of your own interest and access to Navy vessels if you would want to do some experiment on one of them. And so he always had this stipend. And this comes into play in a minute when he was interested, he got reinvigorated in studying the magnetic field and the relationship with these very high energy particles in the solar system coming into contact with the Earth's magnetic field. All right. And so, the topic that Van Allen became interested in after working on the proximity fuse was the distribution of cosmic rays in the Earth's atmosphere. This is a very modern understanding of cosmic rays, and so we have the sun, of course, and we have large ejections of particles. We call it the solar wind, or this is called a coronal mass ejection. It's a high density part of the solar wind. This is the Earth, and the blue lines here represent the magnetic field that threads, that is generated in the core of the Earth, and when you try to draw its effect in the solar system, you can end up drawing these lines that connect positive to negative and kind of loop around. And so as the cosmic rays emerge from the sun, they have two options. They can get deflected around the Earth's magnetic field, or they can get trapped in these magnetic field lines and then radiate. So we're going to come back to this in a minute, but that is essentially what Van Allen helped us understand, our modern understanding of cosmic rays in our solar system. And not just Earth. We're going to see in a few slides that this happens at most planets in our solar system, especially those that have magnetic fields. So one of the ways that scientists were beginning to study the distribution of cosmic rays in the Earth's atmosphere was to take recovered German rockets and to build scientific instruments on them and then basically repurpose them. So it's a very visionary idea of recycling. I mean, people were obsessed by the propulsion mechanisms that had been developed in World War II, especially in Germany. And so here's Van Allen at APL. So this is on the East Coast before he came back to Iowa, but he was involved in these early experiments to design cosmic ray Geiger tubes and detectors that he would try to launch in these V2s. I know, you're right, exactly, absolutely. You're gonna, luckily there's gonna be a few more coming up, but yes, this was, I mean, it's sort of actually amazing. I'm surprised actually that there's even one there. So this is the kind of work that Van Allen was doing when University of Iowa called him up and said, we'd really like you to consider coming back to the University of Iowa and to lead an effort in this kind of work. We think it's very valuable. And so that's exactly what James Van Allen did. And using his kind of Iowa homegrown invention, his knack for inventing things and trying things, he and I think a few others came up with this idea that was better than just a rocket and better than just a high altitude balloon, okay? And so these are devices called Raccoons. It's a name of their own making, which is part rocket, part balloon. And this really became a major area of research in the years right before the space race. And so in the years sort of 1950 to 1960, this was what was going on. And this is a picture from the basement of McLean Hall. This is what manufacturing of space technology looked like then. You don't see anybody in white clean suits. You don't see anything behind locked doors. This was, basically an assembly line waiting for research staff and engineers and students to get involved in integrating the parts into the Raccoon. So this would be, the way these worked is they were quite long, and we'll see an up and down picture of one in a minute. The bottom part would be the rocket propulsion. The top is basically the scientific payload, which consisted of a fairly simple Geiger counter and then some basic electronics. There was no data recording device in this era, and so the data had to be transmitted in real time. And then Van Allen used the connections he had with the Navy to be able to send these Raccoons up. So this is the balloon. So what would happen was the balloon would carry it up 10 miles or so, and then the rocket could get up to 60 or 70 miles up into the atmosphere from launching at a higher altitude. And so they were able to piggyback on various naval ships that were going exploring or doing work at different latitudes to make a more complete picture of where cosmic rays were located in space. And so just a few pictures showing, these are pictures from the University of Iowa archive and also from our department's archive, just showing that Van Allen was very active. So even though he was the chair of the department, he would go on these expeditions. He would train his students on location. They obviously had to take summer courses or something because they would be gone for quite a long time. But this is the size and scope of these balloons that would carry the rockets up. And you can see, this I think is my favorite picture ever, because this is right outside of McLean Hall, right in the middle of the Pentacrest. Nobody has a white lab coat on. They just have their regular clothes, and you can see they have what we call the guts, or the instrument payload here, and they are testing. This is they're testing to see if they can detect, they're testing that with different magnetic fields here. And so, but this is right out in the Pentacrest between the buildings. And then here are some pictures of that row of Raccoons, and you can see the various engineers and students working on getting them integrated and ready to be then go with Van Allen and his team out on ship to be launched. But at the same time, the ultimate quest was really to get higher into the atmosphere and actually to put a real satellite that went around the planet that could actually make these measurements and ultimately make these measurements and record them to be sent down at later times when you weren't in direct contact with a receiver. And so this, and there had been quite a bit of worldwide effort just generally to study the geology of the planet, the atmosphere, the oceans. And so there was a team of international scientists that coined the year between 1957 to 1958 the International Geophysical Year. And this was when things really heated up in terms of the space race. At the same time, of course, and we won't get into the political aspect and the sort of the kind of space war kind of aspect, but there was tension between the U.S. and then the USSR in terms of actually which country was going to put something up first and what was the purpose going to be. Was it going to be for militaristic purposes or spy purposes, or was it going to be for science? And so, as we all know, Sputnik 1 was launched by the USSR in October of 1957. And Professor Van Allen, and again, I won't go into the details here because that's an entire couple of lectures, but the biography of Van Allen outlines this very well. He had been working with, the US they hadn't quite figured out their launch platform. They were trying out a couple of things. And so he was very clever. He knew that any kind of mission that was going to go into orbit should have a scientific instrument on it. So Sputnik did not. Most of you know Sputnik had no scientific instrument. It had a device that made a signal at radio frequencies. So the US definitely wanted to put an instrument in space. They wanted to be the first to have an instrument, but they weren't quite sure of their launch platform. And so Van Allen was clever enough to design, again, a simple enough instrument that it could be adapted at the last minute to either of the platforms that the US was working on. And so I just want to show a clip from this very nice video that NASA made at the anniversary of Explorer. Let's see if we can, this one I don't think was, whoops. Okay, let's just put this up there. Let's go back here. Okay, there we go. All right, let's just watch.
An experiment laboratory.
Oh, here we go. Okay.
Our satellite, and third, the necessary instrumentation to record and transmit the scientific data assigned to this experiment.
So
This
that's
assembly, which is the actual payload for the satellite, contains both transmitters, the necessary circuits for the impact microphone, which will detect the collisions with meteorite particles, and a Geiger counter to measure cosmic ray intensity.
So that was Van Allen's.
At Cape Canaveral, Florida, the Army's Jupiter-C rocket is ready for America's second attempt to launch a space satellite.
The first one,
The
Vanguard,
hours-long
didn't
countdown
work.
approaches zero. A moment of enormous tension, for every missile launching is still an experiment. Any one of tens of thousands of things can go wrong, with catastrophic results. But all that can be done to assure perfection has been done. The moment is at hand. The countdown reaches zero. Close-up of the United States edition of Sputnik was made at a press conference with leaders of the scientific teams. Dr. Werner von Braun, Dr. James Van Allen, and Dr. William Pickering. A three-way collaboration between private industry, academic science, and the military.
All right, so that just gives you a little flavor. That's a nice video if you want to learn a little more about the story. So, so that was a very exciting moment, and Professor Van Allen was, of course, a national hero, and you know, things at Iowa then just kind of took off. Here, as you saw in the video, is kind of a, again, it was, you can see that it was modeled very much on the instrumentation that he used in the Raccoon. So again, the propulsion here, the nose cone with the scientific instrument here, and these had been flown and tested. The guts there had been flown and tested many times on the Raccoon, so it was excellent sort of training ground for the future of the Explorer program. And Explorer 1 was just the first in a whole set of Explorer missions that were designed in the late 50s into the early 60s. Explorer 3 was the first scientific satellite to have a data recorder on board, and that data recorder is actually now, or a model of it is now in the Smithsonian Air and Space Museum. So if you're out there in Washington, D.C., it's really exciting to see that from the University of Iowa. This is a staged photograph. This was when Walter Cronkite, I think, came to the University of Iowa and did a series of staged photographs. He wanted to show the moment at which they made the discovery of these radiation belts, which I'm about to tell you about. And so anyway, this is George Ludwig, who you saw in the video, who was the graduate student who really did the lion's share, the heavy lifting. He actually drove the scientific payload out to California on his own. Van Allen was on I think another trip, and then they all converged at the launch once it was integrated. So the discovery, just to give you a tiny bit of physics, the discovery was that what would happen was that these cosmic rays would get trapped in the Earth's magnetic field, and then once they were trapped in the Earth's magnetic fields, the ones that didn't get deflected around our planet, then they would radiate. They would tend to be concentrated. The magnetic field has a large scope, but they would tend to get concentrated in this belt area. And so they would mirror back and forth on these magnetic field lines, and they would radiate and set off a signal that we could measure with the device. And we now understand that there are many layers of radiation belts. And so some of the more modern research has to do with thinking about the different energies in different parts of the radiation belts and the sort of structure of the radiation belts and what that can tell us about the environment in our planetary system for cosmic particles. And so, but the discovery in 1958 was that there was a structure out there that was larger than the planet that was radiating. And what would happen was the Explorer 1, as it orbited the planet, it would go through periods where it was flying through the radiation belts, in which case the signal was very, very high, and it would actually saturate the detector and have no signal. And then there would be sort of a background level because you're flying out there in cosmic rays. And so the brilliant thing that happened it actually happened in a hotel room, and it was just Van Allen, and he was doing it sort of by his bed table. But I like how they're trying to capture the team aspect of it here. But what they were seeing was the signal drop out at many places, and it was Van Allen who figured out that that must be the spacecraft going through periods of heavy belt activity and then areas where it was missing, and that wasn't actually missing data. I mean, it was missing data, it wasn't a low level. So that was a big year for University of Iowa. That fall, the homecoming button. This is actually our museum exhibit logo, but it said, University of Iowa Homecoming 1958. But this was the actual design, vintage Herky, some Sputnik-like things, the old Capitol on Earth. And then the engineering students' corn monument was, of course, in honor of the rocket. So that was a very exciting time for University of Iowa. This led to just a suite of activities happening in the department. And so here in those days, again, the actual trajectory and the tracking, what you had to have in order to collect the data was you had to have, and keep track of where the spacecraft was, is you had to have multiple places on the planet where you could, where the satellite would go over and communicate with you. So you had to make sure that the trajectory of Explorer 1 was going to fly over places at the right time. And so one of the things when we were working on the museum exhibit that the students discovered was a map of the world, and there were all of these kind of colored pencil and crayon markings on it where they had been mapping the trajectory out over different parts of lands. The students were really, really excited. I had never seen that. The archivist had never seen it, and so the students were thrilled, and it ended up, we showed that in the museum exhibit. This is, I think, a Raccoon, although it kind of looks, I think it might be one of the Explorer ones, but it's a model of something. And again, the scientific payload, some of the other components, and then again, teams of, there's George Ludwig, teams of people that were contributing to this in the Department of Physics and Astronomy. This is a picture of the machine shop, probably looked like when Mike arrived, maybe. And so this is still there. This is now over in the Van Allen Hall, which at the time was the Physics Research Center. So the teaching in Van Allen's time was still mainly happening in McLean, and then at some point the Research Center ended up adding a classroom wing on to the end. But one of the main things in the Research Center was this machine shop with state-of-the-art machines and a team of machinists and technical staff who really, really were able to make this happen. And so this is one of my favorite pictures. This is the housing for a follow-up satellite to Explorer 1. This is the housing for one of the INGEN satellites that in the early 60s was designed, constructed, integrated, tested, all but launched, and then it was tracked and the data were recorded and studied at the University of Iowa. Here's, and these are probably from mixed years. They're not all exactly the appropriate era, but you can see there were many people contributing to the calibration and design and testing of these instruments that would be fitted into a larger housing. So the way that spacecraft work is that unlike Explorer 1, things became more sophisticated. So you would have a slightly larger instrument housing, and you may put multiple experiments inside your instrument housing. And so here are pictures of individual components of instruments that would go into the housing. You'd also need things like navigation equipment and data storage, and various sensors would all be part of these machinery. Here's one of the later INGEN spacecraft, and this is a very young Professor Don Gurnett. Some of us are going to his retirement dinner on Saturday night. He has been at the university for 60 years, both as a major student of Van Allen and as a very, very distinguished professor, bringing in hundreds of millions of dollars to the university over his long career in terms of projects. But this is when he got his start. He was an engineering student who came over, made an appointment with Van Allen. It didn't go quite as smoothly as Van Allen saying, please join. Don had to write a couple of paragraphs about his qualifications, and then Van Allen reviewed them and invited him in for an interview. But it was a very exciting time right after Sputnik to be involved with this work. This is a picture of the North Liberty Tracking Station. This station is still University of Iowa property now, so if any of you go out toward the McBride nature area, you will see a little dirt road to the left, and if you drive up, there's a fenced-in area, and there is a very large dish out there. It's a 25-meter radio telescope that is now part of the National Radio Astronomy Observatory. You have a question? Yeah, right, yeah. There's some funny things out there. So the original tracking station that Van Allen had was bought from a kit, the satellite dish in those days, and then he rigged up, he got the Navy to contribute some parts. And when we put the exhibit together, some of my graduate students and senior colleagues knew the exact model of the parts from what kind of a gunner ship the connector pieces were from. So we have that in the caption at the museum exhibit. So this dish was used for all sorts of different purposes, primarily for tracking and testing. So for testing the instruments to make sure you could communicate with them, the spacecraft, and then also for tracking and some data download later as things got into orbit. This was used routinely until the late 70s, early 80s for Dr. Van Allen and Dr. Gurnett and Dr. Frank's work. And then when NASA took over that functionality, Van Allen looked to his junior astronomy colleagues and said, is there anything you could use this antenna for astronomically? And my senior colleague, Robert Mutel, said, well, there's an effort underway in the US to combine radio signals from dishes in different parts of the country to simulate a large telescope that's the size of our continent. The technique is called very long baseline interferometry. And if anyone watched the news in April, when the first image of a black hole shadow was made, it was using this technique. Not at these wavelengths and not with our dish, but some of the pioneering work that Professor Mutel did, some of the original experiments fed into the technique that was then later used with different telescopes at a much different frequency this spring. So it's a little bit of an Iowa connection there that started at this site. Right now, the National Radio Astronomy Observatory leases that site, and the telescope's part of a national array. So we don't have any priority, although many of us apply and use this facility that's there now as part of our research, but it has nothing to do with the University of Iowa. We do take our students out there from time to time.
There were actually 2 dishes.
Was there another one, Mike?
Yeah.
Where was it?
The first one was down at the hills.
That's right, I had a picture of that.
It was a 28-foot dish. We moved it up there, and we put the 60-foot up.
Oh, fantastic. Yeah, so Mike said that when in the late 60s, there were 2 dishes out there, a smaller one and then a larger one. And were they used in tandem? No, okay. They just had different purposes depending on what they were doing. I mean, this one has a much larger collecting area, so it would have been used for things that were further away, like the tracking and data, and the smaller one may have been used for more short-range testing. So if you go out there, you're right, Mike, you can actually see the mount for the smaller one, I think. No, they took it away. Okay. I've seen some mounts. I've seen some cement mounts outside of the fence where I've been told Van Allen and his team used to put things for testing.
Yeah.
So.
Yeah, that area is still there.
Yeah.
Where this dish was and the other one, the small dish is pretty much where the one that's out there now
is. Okay, right, yeah, and this one's more, but the whole landscape has changed a lot. The trees are much more substantial. So this is a picture of inside Van Allen Hall where data storage and tracking would have happened. So you can see the whole building, and the way the building was designed has a lot of interior space, 4 rooms of equipment like this. Here's some great pictures of, this probably was this looks like it was probably in the Southwest. I don't think this was in Iowa, but this was early testing of one of the spacecraft. And what happened next then, in the late 70s, was that Van Allen had two major proteges, Professor Don Gurnett, who we've talked a little bit about here, and Professor Lou Frank. And what was really great about this team was that they were all interested in space physics, but in different aspects of space physics. So Professor Don Gurnett has had an incredibly successful career studying plasma waves that are generated by the interaction of these cosmic rays and the Earth's magnetic field. Professor Van Allen was interested in the Geiger measurements of the particles, and Professor Lou Frank used a different technique and was interested in the higher energy cosmic ray particles. And so the three of them could all contribute to an individual instrument, an individual spacecraft with different individual instruments. And so this really pioneered the whole idea of the spacecraft that we have today. So here's some women for diversity purposes. There were some women working in the early 70s. So this is Hawkeye, which must have been, was that in orbit when you arrived, Mike? Or yeah, so this was kind of the penultimate University of Iowa full orbiting spacecraft before we built an instrument in the late 70s that flew on the space shuttle. So Hawkeye had instruments representing each of these three research interests, and it was everything was done here at the University of Iowa. Then what happened is the movement, and that was in orbit around Earth. Then what happened was Van Allen and his team discovered that there were this same effect of the interaction between solar wind particles and a magnetic field could happen at the outer planets, because the outer planets actually have much stronger magnetic fields than the Earth. So the two things that guarantee that a planet will have a magnetic field are you have to have a metallic core, so you have to have molten material in your planet's core. So you can imagine as the planets get bigger, like Jupiter and Saturn, their cores are going to be very molten. They may have lower density interior layers, and they may be much bigger, but their cores are going to have more metallic material that is molten than, say, the Earth. The other thing that guarantees you have a magnetic field is that the planet must be rotating, all right? Rotation rate of the Earth is a day, 24 hours. Rotation rate of Jupiter is 10 hours. So you have a massive quantity of molten metal, and it's rotating very, very quickly. So Jupiter has an unbelievably powerful magnetic field. And when we started to look at, when Van Allen and colleagues started to look at signals from Jupiter, they immediately detected essentially radiation belts around Jupiter that are much more substantial and much stronger than the ones around Earth. And so this work was done in large collaboration with Professor Don Gurnett, and he has made his career studying the interaction of the sun's particles with these outer planets, Jupiter and Saturn, on many, many different missions that are too numerous to go over here. But this was sort of a turning point for the University of Iowa, where when spacecraft were being sent out to Jupiter, like Voyagers past Jupiter, they didn't go into orbit around Jupiter, but the Voyagers had plasma wave instruments on them. And then when we started to put spacecraft in orbit around Jupiter and Saturn, the University of Iowa was represented on all of those spacecraft. Here's just to represent Don in celebration of this retirement this weekend, this semester. So here he is as the project manager, as a young engineering student, 18 or 19, because he started college early. And there he is just a few years ago at a scientific conference we had in his honor. So just to sort of reiterate what I just said is that the University of Iowa has a whole suite of instruments in space. This is the inner solar system, and you'll be hearing about a few of these in a few minutes. And then in the outer solar system, we of course had instruments on Voyager 1 and 2, which have now both thought to have left the actual definition of the solar system and be in the interplanetary or interstellar medium. And then we have instruments on satellites that are in orbit around Jupiter and around Saturn. And we have this beautiful list that one of the administrative assistants for the space physics group keeps up. It's not even current, I'm sure, because some of these things have actually launched. But you can see that we started here with the Explorer series, and we had to pioneer. And then these were some of the engine years. And you can see, especially in the early days, there was a lot of failure, okay? And so the machine shop would have made multiple copies of the housings. The instrumentation was relatively simple, even by today's standard. And so you would not necessarily expect that it would work out. And so you can see some of the long history here of doing things both around the Earth and then further out in space. Galileo was around Jupiter. Geotel, Wind, and Polar were around the Earth. Cassini went to Saturn. The cluster satellites were around Earth. We have had a number of missions that have studied Mars, because Mars is now thought to have a very weak sort of remnant magnetic field and a very interesting atmosphere. And so there's quite a bit of work to do there to explore the future of our planet and the past of Mars. And so I thought I'd just take the last couple minutes here to just mention some of the highlights. So we have an instrument on the MAVEN spacecraft. The instrument, here's a copy of it right here. This might actually be the instrument. And this is my colleague, Professor Jasper Halekas. And he is doing some testing of this instrument. And this instrument studies the electrons and or ions that are interacting, that are from the sun, that are interacting with Mars's magnetic field. And they're helping us understand how Mars lost its atmosphere. So when Mars's magnetic field became much weaker, when its core cooled out, then the solar wind particles were able to push on Mars's atmosphere and shed Mars of its atmosphere, so that it lost its atmosphere, and that's what contributed to the end of a comfortable climate on the surface of Mars. And so, these rainbow colors here show velocities of particles that this instrument is measuring, currently even shedding the atmosphere of Mars. When the atmosphere of Mars was denser in the past, this process is thought to be able to contribute to the entire loss of Mars's atmosphere. And so that's work that my colleague Jasper is doing. We also have research scientist Bill Kurth, who has made multiple contributions in this area. One of the most recent instruments that we're so very proud of is orbiting Jupiter right now on Juno. So this is the large spacecraft Juno. This is the large pair of antennae that are studying plasma waves. So when particles interact with Jupiter's magnetic field, they make waves that we can pick up. And this is part of the box that connects the antennae here. And this is an artist's rendition, of course, but you can see Jupiter is thought to have aurora, because aurora are inexorably connected to the magnetic field. And then these lines are supposed to show magnetic field lines, and this pair of antennae will pick up plasma waves that are generated in that structure. And so lots of different people have contributed to the design, build, and testing of just one instrument in a spacecraft that has 8 to 10 different instruments, each built by different groups on it. We also have the Van Allen probes, which are a pair of twins, spacecraft that are really diving into the complexity in the Van Allen belt. So basically going back and redoing Explorer 1, but with all the modern amenities that we have now in the lab. And so the team, just one of the instrument teams, the instrument's called Emphasis, that Professor Craig Kletzing leads. And this is a group, many of these scientists are from our department, and engineers, and then also from other places. So this is the Van Allen probes, which is currently in orbit around the Earth. And then we have a couple of exciting upcoming projects. So this project is a collaboration between a relatively new professor, David Miles, and Jasper Halekas, and this is a sounding rocket that will launch later this year to study the aurora, carrying instruments from the University of Iowa on it. And a lot of students have been involved in this project. Professor Miles has a partnership in Norway and routinely sends undergraduates to spend an intense week called rocket school. It's literally like a rocket boot camp. And so earlier this year, or I think it was last fall, we sent 3 ladies from the University of Iowa, an engineering student and 2 of our undergraduate majors in physics and astronomy, and they wanted to recreate the Explorer 1 photo with a new look. And another project that isn't necessarily in our solar system, but that is studying our galaxy, is a satellite that was, it's a CubeSat, one of these little kind of pre-packaged housings, and then you fill in the instrumentation. The instrumentation was conceived of and designed by my colleague Phil Carrot. This is one of his research students who's going to be a senior, Hannah Gulick, and she is putting the early stages of the instrument into a vacuum chamber to do some testing, because you want to test it under the conditions that you're going to have in deep space. And this instrument is in orbit around the Earth, but it is studying the very nebulous halo that exists around our Milky Way galaxy to try to get a handle on how much matter is there and how much gravitational potential may be there in terms of dark matter, material that's missing. And so these X-rays are helping us come up with the faintest stuff that might be there. So again, just to remind you that this legacy has been left for us, and we are taking full advantage of it. I will just play I'll play 2 short clips, and then I can take some questions. This is just a small interview with Professor Craig Klutzing, who just a few days ago was awarded the largest research grant in UIowa history for the Tracers mission. And so here's a little clip of him talking about.
The idea of magnetic reconnection has been around for quite a while. And the basic idea is that if the sun's magnetic field lines point downward and the Earth's magnetic field lines point upward, when they meet, I can sort of break each of the 2 field lines in half and connect, let's say, the bottom ones to each other and the top ones to each other. And now I've connected a sun magnetic field line to an Earth magnetic field line. And then as it turns out, because there's a solar wind that flows away, those field lines get dragged away from the sun. And in that process, energy gets introduced into the Earth's magnetosphere, and that energy can get transferred to particles, causing things like the radiation belts and things like the aurora borealis. The overall kind of way I often like to explain what we do is with the concept of space weather. People are often told that space is empty, it's a vacuum. Well, that's true, but a vacuum doesn't mean nothing is there. There's just a little bit of something there. But space is so vast that that little bit of something can start to have significant effects over the scale sizes of how big space is. And so what we're really trying to do in the broadest sense is to understand the weather of space. It's hard not to be enthusiastic about this stuff because it's a set of measurements that this region, the Earth's cusp, has not really been focused on. And so both these magnetic reconnection effects, some of the things associated with the aurora that happen in this region, those are probably my 2 predominant interests of the project, and those, interesting enough, form our basic science objectives.
That gives you a little idea about what Tracers is going to be studying over the next few years. As it has been designed and it will be built and then tested at the University of Iowa. And I just want to close by just showing a few images of the exhibit that was in the basement of Old Cap a number of years ago. I think this was my favorite wall because it was called the DesignBuild Wall, where we actually had groupings that were many of the photos you saw today, but we had groupings of photographs showing the different stages of projects, all which had been done at the University of Iowa. And again, you get the idea that this is clearly a team effort that requires many players. So these are some of the artifacts that exist. The University of Iowa archives at the library, at the main library, has these in storage. So there's Engine 3 back there, and here's Hawkeye, and then we have some engineering models. That the far wall back there was sort of the modern era, things that Mike may have contributed to, and then we had sort of a little physics lesson in the middle. And so the exhibit had 3 main parts, and it was really, really fun to put together. And just kind of by way of thanks to Zach and our friends in the Henry County Trust and the UI Archives, we'll just close by playing this kind of fun video about what it was like to do the project using the resources and tools that we had. So I was working with my department and others on campus to put together a museum exhibit that kind of highlighted the legacy and experience and contributions of the University of Iowa to the entire United States space program. And so as part of 2 years of first-year seminar classes, I brought my students into the University of Iowa Archives to look over the many, many boxes of material that supported this very exciting time in U.S. space history. In addition to actually engaging students with individual boxes from the Explorer 1 and Van Allen Papers archive, one of my other motivations for bringing students into the archive was actually to show them that the University of Iowa has a rich archive and that it's a resource that they may use throughout their careers for even other things that they're studying.
It was just a couple boxes presented, and yet there were hundreds of them stored away, and so we were just seeing a glimpse, and yet knowing how much material there actually was just, it was amazing.
Each student in the class, I think Zach will remember, was assigned a box, kind of, somewhat randomly, and so there were a lot of discoveries that just unfolded in that moment. I was looking for things that the students thought would be great to have in the exhibit.
Right, and so one of the coolest things that happened was when someone pulled out a map, and then suddenly it shows the orbits of the Explorer 1 spacecraft going around the world, which is just mind-blowing to just see put in a box right here, and suddenly we're pulling it out and just looking at it. It's crazy.
And the trajectories that were that the students discovered on the map were actually hand-drawn with markers. And so we imagine Professor Van Allen and his research team, composed largely of students at the University of Iowa in the fall of 1957 and early 1958, when there was literally a race to get their instrument launched. They were hand-drawing these things these trajectories on a map.
Once I learned that the Explorer 1 spacecraft instrument was built at the University of Iowa, I just sort of realized, oh, this is the place I should go to study space, because we've been around since the very beginning. We were the beginning of space research in the U.S.
All right, so I think that's probably my last slide. So thanks so much, and I'm happy to take some questions in our remaining time.
So people at home can hear, we have to mic
Sure.
the questions.
Yep.
I just thought I saw something on CNN or something about the shutdown is holding up a very large grant to the university.
I would say, so I'm not sure what you saw on CNN. I think there have been a couple of things this spring that have been in the news. So one was a very large grant that I talked about. I think that I would say the announcement of that may have been a little delayed. We've been anxiously awaiting it all spring. We had a feeling that it might come to us, but you never know until you know. And so I do the teaching assignments for my department, and a lot of times when people get large grants, they need to buy out of their teaching. So I've been anxious to hear, because Professor Kletzing teaches one of the largest introductory physics for pre-med courses in the fall, and I think he's going to do it, because he said the real hard work is going to be in the spring, but I've been waiting to hear for that. The government shutdown, I would say, did affect our department pretty severely. We had a few people have to go on furlough, and we had briefly, and we had a few things rearranged. There were a lot of faculty who were on scientific panels that were delayed, and so there was a little shuffling around we had to do. But the great part about being at a research institution is you can help still get the work done as much as you're allowed to do, and you can support the people that are doing it during those times when the government isn't making good on their promises. So,
do you know, did the university make a video of your exhibit that was in the basement?
We have some good photographs, and there were a couple of news stories that took us through it. I think it was such a labor of love, and it was sort of, it had to be moved out quickly, and so I think we probably should have done a better job archiving it. The vision is to create, well, the real vision would be to have a permanent campus museum to celebrate space and space history. So we're waiting for that to happen. We need some resources for that. A lot of people call and ask us about that. But in the near term, we thought about building essentially a digital version of it. So everything that was in the exhibit, I have in a Dropbox folder. I wrote all the text. There were thousands of words of text, and one could imagine doing a version that's a little less technical. This was an exhibit that was clearly put together for an academic community, and there were lots of people who came out of the woodwork who had worked in our department to see the exhibit, and it was really fun. So we wanted to have all the right technical details for them so that people could, the names were there and the details. It was a typical academic experience where at the opening we were so excited, and then when I got back to my computer that night, there were lots of emails from people whose work had been featured correcting me. I took them very, very kindly, and then we made the changes, but I figured that's what you do, and that's what we do well in academics. So.
Were the Van Allen belts generally thought to exist before the measurements from Explorer 1, or was it a complete shot?
I think there was an idea, and you could actually hear a little bit in George Ludwig's sort of presentation in that old NASA video. I mean, people knew that there was probably some distribution of energy out there. There were a lot of kind of wacky and neat ideas about what it might be. I think people had an idea about what cosmic rays were, but people had not a very good sense of how they were distributed. So the real discovery of Van Allen was this structure, and actually I realized that picture didn't quite do it justice. The real structure is that the number of particles really peaks right in this kind of belt in the central region, and so that was one of the big discoveries there. And now understanding that there's different particle energetics, that the Earth, and as you heard Professor Kletzing say, that the Earth's magnetic field may come in contact with the sun's magnetic field, and that may be an additional source of energy for the particles. That is now our much more robust understanding. But in those days, there was just a very vague notion of some kind of energy out there. And so really quantifying and putting some structure on it was really an important discovery.
All right, any other questions? Okay, Dr. Lang, give us a teaser for what you're going to talk about next month, because she's giving another program for summer.
Yes, that's right.
For us.
So I told you that this is not my area of research, although I've learned a little bit about it by sort of thinking broadly about what's happened in our department all these years. My own expertise is I'm an astronomer, not a space physicist, so that means I study stuff that I don't study the interaction of particles and planetary magnetic fields, which is kind of the domain of space physics. I'm also not a planetary astronomer, which actually studies the planetary properties, but I study our Milky Way galaxy. So we're one star in our galaxy, and we have a bird's eye view to the very center of the galaxy. I don't study the black hole, though I will talk in my presentation a little bit about what we know about that black hole. And now that part of my presentation has changed because we have an image, which is awesome. But I study the rich environment right around the black hole and how stars are made there and what magnetic fields are doing there. And there's some real challenges to observing that region, and I won't tell you what they are. You'll have to come and hear about them. But we can't use optical telescopes, so we have to be much more creative. So I'll be talking about that in July, right?
On Wednesday, July 24th.
So it might be 4 weeks from
Same
tonight.
place.
Yeah.
Yep. So do come back. And thank you all for coming, and thank you, Dr. Lang.
Yeah.